Hello, this is a demo of a point related to the Symmedian point, and in more particular, basically related to our ongoing or our reactivated interest in the most likely position from three LOPs. So if you have celestial navigation, you have three lines of position that look like that, or three bearing fixes that you take with your compass or other means. You end up with this triangle of lines, often called the cocked hat. And the question at hand is, once you have this plotted on the chart, the one measurement in principle told you you're somewhere on this line. The other measurement said in principle you're somewhere on that line, and here you're somewhere on that line. And they don't agree because each of these has errors. Each of the measurements has some errors. And there's various kinds of errors, and that's one of the crux of what we're doing. One of the early studies, in the 1800s, it was established, or the first presented, was the assumption that if each of the lines, each of these LOPs here, have the same accuracy, they have a statistical or random error accuracy. If you did it 100 times, it'd be off by a certain standard deviation and so on. If you make the assumption that each of these are the same, and indeed you make the assumption that there's no fixed error, no common fixed called systematic error that applies to all of them together. That would be, for example, in celestial, you had a index error that was wrong. You said it was a minute off, and in fact it was a minute on. So you have there a huge error, 2 miles, and so forth. And you're assuming you have none of those, and these are equal random errors like that. Then it's mathematically you can show that, or I'll show you what the argument is. The argument is that you're located here at what's called the Symmedian point of the triangle. And we have 2 videos I just put online about how you determine where that Symmedian point is. But for now, the argument that you make to begin with is you make the assumption that the most likely position you're going to be in this triangle is when you are as close as possible to all 3 of them. In other words, you want to minimize the distance between all 3 at the same time. But the point can be out here somewhere, and then this would be, one of these got to be positive and one negative. And so the way to get around that is you say, I'm not minimizing the sum, I'm minimizing the sum of the squares. So there's this you call this, say, x squared, y squared, and z squared, or purple squared, orange squared, and green squared. And then you sum those up, and that's the number you want to minimize. Like, for example, when this guy is sitting right here, here's what these actual distances are in some units. It really doesn't matter at all what units there are. But you see that P, now, what they're calling this, BC. BC is this, so P to BC, that's this one. Distance to BC is 74. And so, and down here to AC, down here, distance to AC. Let's go down here and put it right on there. So AC, where is the distance to AC? Oh no, I'm sorry, not here, up here. So here's P, here's the distances of point P to CA, and that's line CA here. So you see there it's 0, right there is 0. And here, well, it doesn't go minus because it's putting the square. And so there they are. So now what this little app does is we created this just to demo this point, that the Symmedian point is special. And you can then go anywhere in this triangle, like here now, at this point P right here, at this point, cancel. At this point P right here, these are the 3 distances, that's the sum of the squares, but here's what it is over at the Symmedian point K. And you can then, and this is a free app, I put the link in the video here, and you can go dial this up yourself and play around with it and see how And you can change the triangle, to see how the Symmedian point moves and so forth. And then you move that around and when you get, if you watch the top number and the bottom number, you see that's going to end up as smallest is right here. So indeed, this unique point in the triangle, which is discussed other places, this unique point was actually discovered in the early 1800s. Been studied tremendously because it has a lot of amazing properties. But anyway, so you can play with this and so forth. And then other thing you can see here, notice that I don't have to make another one of these and put the centroid in here. But if you put, if you have like this isosceles triangle, then the centroid of that and the K the Symmedian is going to be the same. But but when they're not the same, you see, look at that. When you have one side that's shorter, like the notably shorter, it's always going to go towards the shorter side. And that's effectively because, look, if you get down here like this, well, wait a minute. What am I doing? Hang on. I'm testing this app to see if it's going to break. No, it didn't. Okay. You see, when you get these down here, these two lines here are basically almost like the same celestial line or the same line of position, and you're going to be somewhere on the median of those two, depending on where this is. And so you can look at the physical logic of how this point is where it is and so forth, and why it pops right back in the middle. That's when these are all the same. One of the main things we are working on is to show, well, actually we published it years ago, many years ago in fact, what we have shown is that when these are not equal errors in each of these, then that has a dramatic shift, and the Symmedian point no longer has any meaning at all. But we're going to rejuvenate that and make some more notes about it. All right, that's what I want to do. And then we have a link here. You can play with this to understand how the Symmedian point moves. You see that this way. And also you can see that always, no matter what kind of triangle you make, that point is going to be the minimum in the sum of the squares.